Hi, this is Davies from Weber State University. Today we'll be talking about experiment 30, fractional distillation. And just as an introduction to the lab, first of all, to define what a boiling point is. So if I have a container and I have a liquid in the container, from that liquid I have a certain amount of vapor pressure pushing upward, and I have a certain amount of atmospheric pressure pushing down. So the boiling point is defined where the vapor pressure is equal to the atmospheric pressure. So depending on where you're at what elevation, the boiling point of a liquid may vary. So we're at a higher elevation here in Ogden, Utah than at sea level. So our solutions will boil at a lower temperature because there's less atmospheric pressure. Also, we can take advantage of reduced pressure in distillation. Sometimes what is done is a vacuum system is hooked up to your distillation apparatus, reducing the atmospheric pressure, and you can boil compounds at a lower temperature that way. Okay, so the next diagram depicts the process of boiling and then condensing and then reboiling again. So if I have a solution of benzene boils at 80 degrees, and I have a solution of toluene that boils at 110 degrees. Suppose I have an 80% toluene solution, 20% benzene solution. According to this diagram, that solution would boil about 105 degrees. So the lower line is the liquid line, and the top line is the vapor line. So this is the concentration of the vapor that would come off of that liquid. So the way this works is you come up to this point, it boils at about 105 degrees. So you come over horizontally until you hit the vapor line, drop down. So that would produce a vapor that's about 60% toluene and 40% benzene. If that solution were to reboil, you come up to that point, so that would boil just under 100 degrees, horizontal down, and then you'd have a solution that's about 55% toluene, 65% benzene. And so that process continues on and on until you get all the way to 100% benzene. So each time you boil, condense, and reboil again, that's referred to a height equivalent theoretical plate, so HTP. And this refers to the efficiency of which a fractionating column can separate out a couple of different liquids. Generally, fractional distillation is capable of separating a couple of different liquids that differ in their boiling point between 20 and 30 degrees Celsius. All of the mixtures in today's lab will differ by at least 35 degrees Celsius. Okay, and so some different packing material that might be used in the fractionating column. Commonly, different types of glass are used, either beads or ringlets or small tubes. Porcelain fragments can also work. Today we're going to use steel wool. There's also recently a publication in Journal of Chemical Education where a scrub brush was used, packed down inside that fractionating tower. Essentially, you just need some kind of material that's inert to the solutions that are being boiled and that has a lot of surface area to allow condensation and then the solution to be redistilled. So here is a diagram of the apparatus that you'll assemble and use for your fractional distillation. So here is your distilling pot, and as you fill it up, and this holds true with any time you're distilling anything, you want to make sure that the round bottom flask is no more than 2/3 of the way full. Otherwise, as it heats, you'll have a flow of liquid that will shoot over the top. Okay, and don't forget your boiling stick. Also, a boiling chip could work in this case. And then on top of your boiling pot, you have your fractionating tower, and you have your packing material that's placed in the center of the fractionating tower. So we'll just pack our steel wool inside here. We want to make sure it's not packed so tight that it's difficult for anything to come through, but we do need enough packing to provide those theoretical plates to allow the solution to boil and then condense and reboil again. Okay, and then up here, as you place your thermometer in, you want to make sure that the bulb of the thermometer is just below the neck of this portion of the apparatus. Okay, sometimes if the thermometer bulb is too high, then you'll have a lower boiling point that you'll measure. Okay, and then you have your condenser that's hooked on next. You want to make sure that the water is coming in the bottom and then out the top. Okay, that allows for complete filling of the condenser. And you don't need a very strong flow of water. Just a trickle of water is all you need to make sure that you have a circulation of the water. That connects in, and drops into your graduated cylinder, and this should be in an ice water bath. The solutions that you'll be distilling, most of them will be very volatile, and so this will prevent some of the loss of the solution due to evaporation. Okay, we want to make sure that the apparatus is sealed tight every step of the way. At each joint, we'll seal it with vacuum grease also to make sure that we don't lose any of our mixture through any leaky joints. Okay, and then this next diagram is what you should observe as you do your distillation. Starting at room temperature, you'll see a gradual incline until you get to the boiling point of the first component of your binary mixture. Then you'll have a plateau. All of the energy will go into the distillation of that first component. Once you get to the end of the volume of that first component, you'll observe one of two things. Either the temperature will steadily rise up to the temperature of the second component, or you may see a drop in temperature at this point. So you've distilled all of your first component, and then there's no solution to be placed on the thermometer, and so you have a recording of a drop in temperature. So all of the energy at that point is going to be put into the pot, increasing the temperature of the pot solution to the boiling point of your second component. So you'll see a gradual incline till you get to the boiling point of the second, and then a plateau. So with your distillation, as you start out, I take the first few drops of A, put it in a separate test tube, and then collect all of the remaining of A into a second test tube. This represents a more pure sample of A for your analysis by the refractive index. And then same thing for B. Take the first few drops of B, put this in a third test tube, and then after that, everything else in there should correlate to component B. And so you should end up with two fractions that are relatively pure for your refractive index analysis. As you complete the lab, you're going to be asked to determine, one, the boiling point of each of your components and the relative ratio of A to B. To determine the actual volume of A, go ahead and add the volume of the first few drops of A with the fraction that was relatively pure. And same thing over here, the few drops that were collected on your incline, combine that volume with your B to get your relative ratio. Relative ratios should be in the order of 1:1 or 1:2 or 2:1. The first thing that we're going to do is we're going to dump out the sand out of our sand bath. Then as we place a round bottom flask in the sand bath, notice I've also added my boiling stick as well. And I'm going to submerge the round bottom flask deep inside the sand bath. That'll allow a lot of heat conductivity. Then I'll add in sand to fill in all the gap. Okay, and then here's my steel wool, and I'll pack that inside my fractionating tower using a spatula. Okay, so when it's finished, it should look like so. Okay, and then add just a thin strip of stopcock grease. Turn it in a circle, make sure it's coated on all sides. Okay, and then angle joint or bent joint. Once again, we'll put a little bit of stopcock grease on each of these connections. We'll rock it back and forth, make sure I have a good connection there. We'll add a clamp at that point. Then the thermometer adapter. Condenser. Stopcock grease again. And this last joint. Connect it there. And so on the bottom, I want the inlet. Make sure the hose is on there secure. And then the outlet goes on the top. As I place my thermometer in, I want the bulb to be just below the elbow joint here. About there. I'll test my water. Okay, so that's probably sufficient. Put wire gauze here to support my round bot or my ice bath. Probably want to bring this up a little bit. Okay. Now we'll go ahead and turn on our sand bath. And I'll start by turning the variac up to about 4.5. As the solution is boiled, there's a reflux ring that's climbed up the fractionating tower. Okay, now I have my first few drops coming over. Okay, and well, I really need to put this in here. Okay, and we'll keep track of our temperature. We're about 43 degrees. Okay, and I've collected about first few meals. Okay, and it'll just plateau at this temperature until all of the first component is distilled over. So the rate of your distillation, you want to drop every 1 to 5 seconds, 1 to 2 seconds. So we're up to 46. Okay, so it looks like there's a slowing on the boiling or the distillation. So we're about 48 degrees, and my volume is about 10 milliliters. So I'm going to go ahead and go to my third fraction here. So the temperature's starting to climb. It's now up to 60. I'll collect a few drops here. You want to put a cork on the fractions you've already collected. Yeah, so temperature is climbing rapidly now. I'm at about 70 degrees. Go ahead and raise this up a little higher. So about 1 milliliter into my second fraction, I'm to about 74 degrees. I know that everything left in here is my second component. The only question is where the plateau will occur, just to see how high. my temperature will go. It looks like it's holding fairly steady at about 74 degrees. Okay, so after about another milliliter, I'm still at 74. So that looks like my second plateau. So my two boiling points look like 46 degrees and 74 degrees. I'm going to go ahead and turn off the sand bath. Allow this to cool down. I can go ahead and remove the heat. Allow that to cool. Okay, so my major fraction here, this is my first fraction, and I would use a sample of this for the refractive index. But for calculation of my total first volume, I would use all three of these test tubes would represent fraction A. So to calculate the volume, okay, and I would take a sample of this as my second component for my refractive index to identify my unknown. But to determine my volume, I would combine the volume for this fraction, this is the first few drops as the temperature increased, with this, and whatever else is left in the boiling pot. So once again, just in conclusion, I have these three fractions that correlate to component 1, these two fractions that correlate to component 2, along with whatever else is left in the boiling pot. At this point, I would just go ahead and take refractive index of the pure samples. So this is where it had plateaued. Take a sample from there for component 1. I take a sample from this fraction to determine the refractive index for component 2. And then to calculate the entire volume, I would just go ahead and measure out the total volume of what's in the pot and these two fractions for component 2. And then I'd add all of these three together to get the volume for component 1. And it may not be exactly 5 to 10. If it were like, it looks like I have more of my first component than the second. And so it looks like it's going to be about a 2-to-1 ratio. Twice as much of the first component as the second. Okay, so for my first component, the temperature that I recorded where it had plateaued was 46 degrees. So once you calculate in the change in the altitude and the lower atmospheric pressure at our altitude, that would be bumped up to around 50 degrees Celsius. And then on the 74 degrees Celsius, for my second component where it had plateaued, that would be adjusted to around 80 degrees for the plateau. So make sure you take care of the change in altitude correction.